Hey guys, welcome back to my channel, MathSprint, and you are watching the 10th video of my calculus crash course. Today I'm going to be explaining some of the thing about definite integrals and applications of integration. Now, before we begin, make sure you're familiar with at least these concepts, which will be very important if you want to understand this chapter in calculus. So first understand these concepts and then continue with this video. The topics to know are basic algebra, trigonometric identities, polynomials, sets and set notation, basic coordinate geometry, how to plot a graph on a Cartesian plane, functions, limits, and continuity, differentiation and its fundamental rules, how to perform differential calculus on different types of functions, the definition of an integral, basic rules of integration, and the fundamental strategies for integration. Now, if you want to understand the fundamental strategies for integration, you can check out my previous video in this playlist, which covers things like U substitution, integration by parts, and other similar topics. Do note for this video, I'm only working with real numbers and not imaginary numbers. All right, so let's recall the concept of Riemann sums. If you want to learn about Riemann sums, you can check out my 7th video on this playlist, which also covers these topics. All right, so when we're working with rectangular Riemann sums in general, the formula for the sum is the summation of all products of f of xk and delta xk, where k is all positive integers till n. So remember how when we increase the number of rectangular strips, the width of each rectangular strip, that is delta xk, becomes smaller and smaller and approaches 0. So this causes our approximation for the area to become more and more accurate. When delta xk approaches 0, it becomes infinitesimally small in value. So we can say that delta xk is equal to dx. And remember, dx represents an infinitesimally small change in x. All right, so in the 7th video of this playlist, I defined what a definite integral was exactly. So let me refine this definition a little bit. A definite integral can be considered as the limit of a Riemann sum. So as the number of rectangular strips, that is the variable n, approaches infinity, the Riemann sum approaches the integral of f of x with respect to x over the interval a comma b. Now also consider this. If the subintervals we choose for the rectangles that I'm saying, if the subintervals we choose are of equal width on the interval a comma b, then delta xk is the same for all values of k. Delta xk will be equal to delta x, which is a general term. Delta x will be equal to b minus a divided by n, because think technically speaking, it'll be like a sort of average change. The set x0, x1, x2, all the way till xn divides the interval a comma b into n equal subintervals, where if you think about it, since the lowest term in this interval is a and the highest term is b, x0 is equal to a and xn is equal to b. So if x1, x2, x3, all the way to xn are the x values for the right edge of each subinterval, then if you think about it, xk is equal to a plus k times delta x. So plugging this whole thing into the equation, we end up with the general formula at the bottom of this slide. So what this formula tells us is that any summation of the form on the left-hand side of the equation can be expressed as an integral like on the right-hand side of the equation. Okay, so before we move on, just something important to note about Riemann sum specifically. I did mention this a little in the 7th video of this playlist. Suppose we wanted to compare each of the Riemann sums with integrals. We would find each of the following. So if f is an increasing function over the interval a comma b, then the definite integral, which is equal to the actual area under the graph, is greater than the left Riemann sum and less than the right Riemann sum. And if f is a decreasing function over the interval a comma b, then the definite integral is less than the left Riemann sum and greater than the right Riemann sum. And if the graph of f is, say, concave down, that is f double dash of x is less than 0 over this interval, then the definite integral is greater than the trapezoidal sum and less than the midpoint sum. And suppose if the graph of f is concave up over the interval a comma b, then the definite integral, which again is equal to the actual area under the curve, is greater than the midpoint sum and less than the trapezoidal sum. Okay, so let's get into the fundamental properties of definite integrals. The first one is pretty straightforward. When you need to integrate a constant k multiplied by a function, then you can take the constant k outside the integral sign. Now for the second one, doing definite integration on a function f of x when the interval for x is only x is equal to a will just get you an answer of 0. So if you think about it visually when you're finding the area under a graph, you should be able to see how this works. Now for the third one, essentially the definite integral of f of x with a lower limit of a and an upper limit of b can be changed into a new definite integral of f of x with an upper limit of a and a lower limit of b multiplied by -1. So for this third property, you might want to pay attention to the way the limits on the integral flip when you add the negative sign. Pay attention to that. Now for the fourth property, you can express essentially any definite integral as the sum of two new definite integrals, and here c can hold any value between a and b. For the fifth property, it basically states that any integral whose integrand is the sum or difference of two smaller functions can be split into two smaller integrals. Now keep in mind, for this fifth property, there's no value labeled c here. That's between a and b. All right, the sixth property. So geometrically speaking, the property implies that the area under any curve of any shape is equal to the area of some rectangle with a length of b minus a, that is the width is b minus a, and the height of the rectangle will be f of c, where c is just some specific value between a and b, which you have to figure out by calculation. And the seventh property states that if f of x is less than or equal to g of x for all values of x within this interval between a and b, then the definite integral of f of x with respect to x is less than or equal to the definite integral of g of x with respect to x. Okay, so now the average value theorem. If a function f is integrable on the interval a comma b, then the average value of f of x from a to b is expressed as 1 by b minus a multiplied by the definite integral of f of x with respect to x. Now, if we're talking about an integral where the upper limit is positive infinity and the lower limit is negative infinity, then there's no actual average value of f of x. But when the limits are some real finite value, f of x can have a real average value over a specified interval of x. Now, you might be wondering, what exactly do we mean by the average value of x? So you remember how the formula for the average, generally speaking, the formula for the average is the sum of all the values divided by the number of values in the set. Well, in calculus, there's an analogous form. Instead of summing our values, we integrate values, and then we divide it by the interval's range. So the definite integral of all of those possible values divided by the range of the interval, is the average value of that function. Now, if you think about it, you can rearrange the terms so that the definite integral of f of x is now equal to the average value of f multiplied by b minus a. So now keep something in mind. Don't confuse the average value of a function with the average rate of change. Those are separate concepts, and if you want to know more about the average rate of change, which has to do with differentiation, you can check out my sixth video of this calculus crash course. All right, let's move on to the first fundamental theorem of calculus. There are multiple ways of expressing this theorem. Now, why is this theorem important? Because it shows the essential link between differentiation and integration. So if f is continuous on a comma b, then the definite integral of f of t with respect to t is differentiable at every point of x. Then f of x is equal to the derivative with respect to x of the integral of f of t with respect to t. So essentially, what this is saying is any function can be expressed as the derivative of an integral. Keep in mind, x and t are both variables here, but a is a real constant, like 0. It could be 0, 1, or 2, or anything. In reality, the value of a is kind of irrelevant when employing this first fundamental theorem of calculus in actual problems. All right, so check the examples at the bottom of this slide. Let's say you have to differentiate with respect to x the definite integral of cos t with respect to t. The limits on the integral are minus pi and x, and this whole thing will be equal to cos x. Now let's say you have to differentiate with respect to x the definite integral of cos t with respect to t. But here the limits on the integral are, the lower limit's going to be x squared and the upper limit's 0. So now what you got to do is you got to use a third property of integration. If you haven't noted it down, you may want to pause the video right now and go back. I've labeled the third property of integration with the number 3. So you then use the chain rule of differentiation, and you end up with the final answer of minus 2x cos x squared as your result. Now keep in mind, for definite integration, always you do not need to add the constant of integration, because always in definite integration, the constant of integration gets cancelled out in the process. Okay, so now the second fundamental theorem of calculus. So now that we already know that the indefinite integral of f of x with respect to x is capital F of x plus c, where capital of f of x is the integrated function and c is the constant of integration. Now, what exactly does this theorem say? If f is continuous on the interval a comma b, and lowercase f of x is equal to capital F dash of x, then the definite integral of lowercase f of x with respect to x is capital F of b minus capital F of a. Now keep in mind, a and b are real constants, so uppercase f of x is the integrated function. So when you plug a real value like a or b into the function, you should get a real value. Now you may be wondering what the uppercase f of x in square brackets is for. This is a form of notation used in definite integration. So what it means is that you have to plug in the values of b and then a and then take their difference to get that definite integral to be evaluated. So the second fundamental theorem of calculus is important because it says that the definite integral of f gives the net change in uppercase f as x changes from a to b. All right, so let's do some sample problems. The first one, we got to integrate x cubed with respect to x for the interval 0 comma 4. That is, x is between 0 and 4, inclusive of both 0 and 4. Recall the fundamental rules of integration here. If you want to revise them, you can check out my 8th video of this playlist. So the integral of x cubed with respect to x is x to the power 4 divided by 4. Now remember what I told you earlier, the square brackets used here are a form of notation saying you have to plug in the values in the top right and bottom right brackets and then take their difference. Now keep in mind you have to plug in the top right number first and then plug in the bottom right number. So when you plug in 4 and then you plug in 0 and then you take their difference and then you simplify, as I've shown over here, you end up with an answer of 64. So now the second question. We need to find the value of f of 1 using the following information. So we know that f of 0 is equal to 7 and that the definite integral of f dash of x with respect to x over the interval 0 comma 1 gives a value of 10. Okay, so we know that the second fundamental theorem of calculus is f of 1 minus f of 0 is equal to the definite integral of f dash of x with respect to x with a lower limit of 0 and an upper limit of 1. That's what the second fundamental theorem of calculus implies. So when we rearrange the terms, you will find that f of 1 is equal to f of 0 plus that definite integral of f dash of x with respect to x. So in that sense, we just add 7 and 10, and we end up with an answer of 17. So f of 1 is equal to 17. All right, so areas of plane regions. So a quick recap on this. I mentioned in earlier videos as well. A plane region would be essentially a two-dimensional space. So pretty much if we let the function f of x be continuous and non-negative on a comma b, the area under the graph of f of x is the definite integral of f of x with respect to x. So essentially, if you look at the graph on the right, the area of the gray shaded region is equal to the definite integral of f of x with respect to x with the lower limit of a and the upper limit as b. Okay, so let's do a sample problem right now. Find the area under the curve with the equation f of x is equal to sine x from x is equal to 0 to x is equal to pi by 3. In other words, this question wants us to evaluate the definite integral of sine x with respect to x, with the lower limit is 0 and the upper limit is pi by 3. So the integral of sine x with respect to x is minus cos x, based on the rules. We know that minus cos pi by 3 is equal to minus half, and that minus cos 0 is equal to minus 1. Now, since two negatives make a positive and 1 minus 1 by 2 is just 1 by 2, we end up with the final answer of 1 by 2, which is equal to zero point 0.5. So what does this mean? The area of the gray shaded region, which is shown on the right here, is exactly zero point 0.5 square units. Okay, so the area of the region below the axis. So far in the problems that I've shown you, we've always worked with an interval where the graph of the function was in the positive, like it was above the x-axis. But what if it was below the x-axis? So in the negative y-axis region, like typically in the third and in the negative x-axis, we have f of y is less than 0, and in the negative y-axis, we have f of x is less than 0. So geometrically speaking, the shaded region, the shaded area above the curve and below the x-axis equals the negative of the definite integral of f of x with respect to x with a lower limit of a and an upper limit of b. So the integral with a negative sign will yield a positive number. Also, here area of the regions above and below the axis. Take a look at the diagram on the right if you want to follow this. So note that the letters A, C, and B are all possible real values of x. So the gray region above the x-axis has an area of A1, and the gray region of below the x-axis has an area of A2. Remember, A1 and A2 are always positive for geometric reasons because it's impossible to have an area that's negative. Area always has to be positive, geometrically speaking. Remember the fourth property of definite integrals, which I told you about. I have shown this property at the top of this slide, where essentially the definite integral of f of x over the interval a comma b is equal to the sum of the definite integrals over the intervals a comma c and another definite integral over the interval c comma b. So now here's the problem. Part of the red curve lies below the x-axis. This means that the definite integral of f of x with respect to x with a lower limit of c and an upper limit of b by itself will have a negative value. Let's suppose we tried to find the total area of both the gray regions by using the definite integral of f of x with respect to x with a lower limit of a and an upper limit of b, which I showed you on the top left. So for this curve shown on the right, because it lies above and below the x-axis, this integral will not be equal to a1 plus a2. That is, the integral of f of x with respect to x with a lower limit of a and an upper limit of b. It will not be equal to a1 plus a2, but rather it will be equal to a1 minus a2, as per the fourth property of definite integrals. So this does not actually help us at all. We want to find the total area of both the gray shaded regions, which is equal to a1 plus a2. Our integral is giving us a1 minus a2, so that makes it won't be applicable in this case. So how do we do about this now? Well, we take the absolute value of f of x. In my first video of this playlist, I talked about how graphs of absolute functions look, though those graphs change so that they never have to go below the x-axis. And at the same time, the shape of the sections of the graph that were formerly below the x-axis do not change. Those sections of the graph just get flipped, or they kind of get mirrored above the x-axis. So for the graph of the absolute value of f of x, also called the modulus function, the total area of the gray regions would not change numerically. So if f is continuous, then the area between the graph of f on a comma b and the x-axis is given by the integral of the absolute value of f of x with respect to x with a lower limit of a and an upper limit of b. So a general rule is over any interval a comma b for which f of x is less than 0, the absolute value of f of x is equal to minus f of x. The area between the graph and the x-axis is the definite integral of f of x with respect to x with a lower limit of a and an upper limit of c minus the definite integral of f of x with respect to x with a lower limit of c and an upper limit of b. So in other words, in order to find the sum of the areas a1 and a2, that is, if you want to find a1 plus a2, you need to subtract the two integrals of corresponding to both those areas. Okay, so now the area between two curves. So let's take a look at the graph on the right. Suppose we wanted to find the area of the gray shaded region, which is the region bounded by the red curve and the blue curve only. If the functions f and g are continuous on a comma b, with f of x being greater than g of x being greater than 0 on a comma b, then the area between the graphs of f and g from a to b is the definite integral of f of x minus g of x with respect to x with a lower limit of a and an upper limit of b. So if you think about it, if you want to find the area of the region bounded by two curves, it makes sense that you have to actually take the difference between the integrals because you have to take a larger area, subtract the excess area to get the area you want. But what if you have a problem where the functions are given but the graphs are not visible? Well, you have to take the absolute value of the entire integral. This way, it doesn't matter whether f of x lies above the graph of g of x or whether the graph of f of x lies below the graph of g of x, because either way, you're going to still get the same final numerical value for the area of the gray region. However, suppose you have a graph that lies where the area of the bounded region lies partially above the x-axis and partially below the x-axis, or even the graphs are entirely below the x-axis. Then what do you do? Well, you have to do the same thing. Use this formula with the absolute value sign around the integral. There should be no difference in your answer unless you make a mistake in your calculation. All right, so let's do a sample problem. Find the area of the region bounded by the graphs of f of x is equal to 5 minus x squared and g of x is equal to x minus 1 whole square. You should not need the graphs to do this problem, but I have shown them here for your understanding. The red curve has an equation y is equal to 5 minus x squared, and the blue curve has the equation y is equal to x minus 1 whole square. So first, if we want to create our integral, we need an interval with a lower limit and an upper limit. So in this problem, the lower and upper limits are the x values of the intercepts of the graphs. So those intercepts are like the corners of the bounded area, if you think about it. So let's find the points of intersection. We do this by equating f of x with g of x using algebraic manipulation and factoring like I've shown here. You will find that the x values of the intercepts are x is equal to minus 1 and x is equal to 2. It's not necessary, but you can plug those into the function to know the corresponding y values. Okay, so our points of intersection are found to be minus 1 comma 4 and 2 comma 1. So now our upper limit of our definite integral will be 2 and our lower limit will be minus 1. Now we form the definite integral of f of x minus g of x, and we can expand the equation and express it as 4 plus 2x minus 2x squared. Now we integrate. You should be able to recall the fundamental rules of integration. And if you can check out my 8th video of this playlist if you want to refresh your understanding of the fundamental rules of integration. So integrating 4 plus 2x minus 2x squared with respect to x gets us 4x plus x squared minus 2 by 3x cubed. So remember, you do not need to add any constant of integration when you're doing definite integration. So now you substitute the upper limit as 2 and the lower limit as minus 1, calculate the difference, and we get a final answer of 9. So what this says is that the area bounded by the red curve and the blue curve, that is this kind of shape in between them, is exactly 9 square units. All right, let's do another practice problem. We need to find the area of the region bounded by the graphs of y is equal to f of x and y is equal to g of x over the interval pi by 4, comma 5 pi by 4. F of x is equal to sine x and g of x is given as cos x. So on the right, you can see the graphs of y is equal to sine x in red and y is equal to cos x in blue. So now we formulate our integral. We know that these are continuous functions, so only a single definite integral is needed. Our lower limit's going to be pi by 4, and our upper limit is going to be 5 pi by 4. So integrating sine x minus cos x with respect to x gets us minus cos x minus sine x. Plug in the upper limit and then the lower limit, and then you take the difference, and you will get an answer of exactly 2 root 2, or 2 times the square root of 2, as the area of bounded by the red curve and the blue curve. That is the area in between them. So using symmetry, this is just something to note. At times, integrating over the entire interval can yield a value of 0. This is used to the effect this is due to the effect of symmetry, where the region which has a positive integral sort of cancels out the region which has a negative integral. So what we do is we calculate using integration the area of one sector, then multiply it by the number of those congruent sectors. That will give us the total area of the shaded region, or the area bounded by the curve. Okay, so before I move on, I would like to revise the concept of cross-sectional areas. So the cross-sectional area is the area of a two-dimensional shape that is obtained when a three-dimensional object is sliced perpendicular to a specified axis at some point. So the diagram on the right shows the cross-sectional area pretty accurately. The gray square here is actually representing a thin slice of the larger rectangular prism. And the sum of all of these thin slices, all of these smaller areas with their own tiny thicknesses, all of these smaller cross sections can be added together to get the total volume. Now you can check out the formula below for your understanding. Alright, so let's move on to the volume of solids with known cross sections. So it's possible to calculate the volume of a three-dimensional shape using integration. Now here's one way of finding the volume of such shapes. Now, what type of shapes I'm talking about? Now, take a look at the image on the right. Now, if you think about it, kind of looks a bit like a croissant, but what it really is a 3D shape with a semicircular base and consisting of triangular cross sections. Also, the cross sections are such that the height of each triangle is equal to the triangle's base length. So, how do we find the volumes of these kind of complicated 3D shapes? So if the area of a cross-section of a solid is known and can be expressed in terms of x, then the volume of each slice, delta V, can be determined. The volume of the solid obtained can be determined by letting the number of slices increase indefinitely. So the slices are taken perpendicular to the x-axis or some other specified axis. So that delta V is equal to a times delta x, where a is a function in terms of x for the area of the cross-sectional slice, and delta x is the width or thickness of each slice. Using calculus and the above concept, it's possible to create various 3D solids with irregular shapes mathematically and calculate their volumes and surface areas. So let's do a sample problem. A three-dimensional solid has a circular base. The equation of the circular base is x squared plus y squared is equal to 25. So actually, from this equation, we should be able to figure out that the radius of this circle is 5, because if you don't know the formula for circles in a Cartesian plane, you should know that it will be equal to x minus a whole square plus y minus b whole square is equal to r square. Here, r is the radius of the circle. So since r square is equal to 25, we can figure out that the radius is equal to 5 units. So all the cross sections that we're using are parallel to the x-axis, and they're all square shaped. So with a square, keep in mind that the all the four sides are equal. So if you think about like the height of the square is equal to the base length of the square all the time. So our goal is to find the volume of this 3D solid. So take a look at the diagram on the right. You see the circular base at the bottom. It has like a green outline. The square-shaped cross sections lie on top of it. Now here I've only shown one cross section for simplicity. Do understand that there will be multiple, and they all will have a thickness of being that's really, really small. So here's something to note. The question said that all the cross sections are parallel to the x-axis, which means the face of each cross section must be parallel to the x-axis. So now look at the diagram carefully. If you notice, the length of each square is 2y. Because we assume that the square spans the entire chord of a circle, so if you don't know what a chord is essentially a line segment where both endpoints lie on the circumference of the circle. So what we know is that the thickness of each cross section is very small, so we're going to let it be delta x. We know the area of a square is the square of its length, so we'll let delta v be equal to the volume of each square-shaped cross section. The cross-sectional area is 4y squared, and the thickness is delta x. Since delta V is equal to the cross-sectional area multiplied by the thickness of each cross-sectional slice, we find that delta V can be expressed as 4y squared times delta x. So now the volume of the entire solid V is equal to 2 times the definite integral of 4y squared with respect to x, with a lower limit of 0 and an upper limit of 5. So why are we integrating with respect to x and not y? Because our cross-sections must be parallel to the x-axis as per the question. So y is our upper limit 5? Because the radius of the circle is 5, which we can figure out from its equation. Why are we multiplying the integral by 2? Well, our lower limit is 0, so if we have, since this integral that we created only covers half of the circle, we need to multiply the integral by 2 to cover the entire circle. This is an example of the concept of symmetry that I spoke about earlier. Since integrating over the entire domain of the circle will give us a definite integral value of 0, because since half of the circle lies above the x-axis and half of the circle lies below the x-axis. Apologies, half of the circle lies to the right of the y-axis and half of it lies to the left of the y-axis. So that'll give us a definite integral of 0. So we have to take the integral for half the circle, which will yield us a positive value, and then multiply it by 2 using symmetry. And that'll give us the positive value we need. So we substitute y for the square root of 25 minus x squared. We can choose minus 20 square root of 25 minus x squared if we want, but that will just give us a negative value for the area, which does not look that good, honestly. So we'll just evaluate the definite integral, and we'll find that the area of this 3D shape is exactly 2000 divided by 3 units square. All right, solids of revolution. So these are another type of three-dimensional shape that can be formed graphically. A solid revolution is a 3D shape formed when a 2D plane region is revolved about a fixed line called the axis of revolution. So take a look at these images. First, look at the bottom image. Ignore the red line for now. We have a blue curve with an equation y is equal to f of x. Suppose we rotated this curve about the x-axis. We would get a 3D shape that looks actually a lot like a flower vase. The red curve is just a reflection of the blue curve across the x-axis. So now take a look at the image on the right. We have a curve that looks to be exponential in nature with equation y is equal to f of x. So when we rotate this curve about the x-axis, we actually form a 3D shape that looks a bit like a cup or a funnel. So using calculus, we can find the volume of these solids of revolution. Let's review the two major methods to obtain the volume of the solid of revolution. Okay, so the first one is the disk method. That's one way. The region under the curve and x-axis is revolved around the axis of rotation, which in this case is the x-axis, forming a solid of revolution. So look at the image on the top right of the slide. You can see that we have a rectangular strip, like that's dark in color, a sort of a rectangular sector of sorts. It has a height of r and it has an infinitesimally small width delta x. Now look at the points x is equal to a and x is equal to b that lie on the x-axis. The length of this entire solid of revolution is going to be b minus a. So now look at the image on the bottom right of this slide. You can see how one 2D rectangular strip generates a 3D solid disk by being rotated about the x-axis. The radius of this solid disk is just r, which is also the height of the rectangle. The volume of this one circular disk is delta V. Now, you know that the area of a circle is just pi r squared. So the thickness of this circle is delta x. The thickness of this disk, sorry, is delta x. And delta v is equal to pi times r squared times delta x. Now suppose you have many of these rectangular strips which get rotated about the axis of rotation, which in this case is the x-axis. You have to add or sum up the volumes of all these smaller disks. Therefore, the total volume of the solid of revolution v is given by pi times the definite integral of r squared with respect to x with an upper limit of b and a lower limit of a. Now, the washer method. In general, a washer is a disk with a hole in it, so that's what it pretty much is in the real world. But how does this relate to solids of revolution? So typically the washer method is used when our solid of revolution is formed because of two curves that intersect each other. The region bounded by the two curves that intersect each other is revolved around the x-axis, forming a solid of revolution. I'll explain this a little bit further. So look at the image at the bottom of this slide. You look carefully where A and B are both located. Always focus on that interval, which in the diagram is between A and B. Avoid considering anything outside the interval unless it's relevant. That's just some general advice. So here's a dark rectangular strip in the region bounded by the red curve and the blue curve. So what is this height of this rectangular strip? It is capital R minus lowercase r, where capital R is the height of the outermost curve within the interval a comma b, and lowercase r is the height of the innermost curve within the interval a comma b. So what happens is this one rectangular piece, which does not touch the axis of rotation, generates a sort of loop around the axis of rotation. And this loop is actually a solid washer. So the volume of each of these washers is delta V, and it's given by del pi times delta x times r square cap times uppercase r square minus lowercase r square. So keep in mind how to distinguish between uppercase r and lowercase r on this graph. Uppercase R is the length of the vertical double-sided arrow that reaches from the axis of rotation to the outermost curve, which in this case is the red curve, as shown in the diagram. And lowercase r is the length of the vertical double-sided arrow that reaches from the axis of rotation to the innermost curve on the interval, which in this case is the blue curve. Now, suppose you have many of these rectangular strips that get rotated about the x-axis. You have to add or sum up the volumes of all of these thinner washers. Therefore, the total volume of the solid of revolution V is given by pi times the definite integral of the capital of uppercase r square minus lowercase r square with respect to x, with an upper limit of b and a lower limit of a. Alright, so here's another concept, the length of a curve, also called the arc length. So graphs can take multiple shapes in general, and if we wanted to find the length of the curve that forms, we cannot just take a ruler and just measure it directly. There's a general formula for the length of a curve on a Cartesian plane. If the derivative of a function f is continuous on the interval a comma b, then the length s of the curve with the equation y is equal to f of x from x is equal to a to x is equal to b is given by the definite integral of the square root of 1 plus dy by dx whole square with respect to x. Now, you may probably be able to notice this, but actually this integral was more or less derived with the help of the Pythagoras theorem. All right, but suppose if a curve is actually defined parametrically, we use the formula at the bottom of this slide. If you want to know a little bit about parametric equations, I introduced them in the 6th video of this playlist. All right, so now a bit about one-dimensional motion or rectilinear motion. So I introduced the differentiation aspect of this topic also in the 6th video of this playlist, so you can check it out. Now, I will be talking about in this integration aspect of this topic. Essentially, we have a particle or some body moving along a straight line. There are functions s of t, v of t, and a of t, which respectively represent the displacement from the origin, the velocity, and the acceleration of the particle, all as functions of time. At the top of the slide, you can see essential formulas here. Keep in mind s of t2 minus s of t1 is the net change in position or displacement from time t1 to t2, and also v of t2 minus v of t1 is the net change in velocity over from time t1 to time t2. Now at the bottom of this slide, you can see the definite integral that is for distance. Remember, distance and displacement are not the same concepts. Distance is dependent on the path taken by the particle, and displacement is just a change in position or location, making it independent of that path taken and only dependent on the initial and final locations of the particle. Thank you guys. That'll be the end of this video. Make sure you hit those like and subscribe buttons to see my future videos on mathematics. Until then, stay tuned.